the topic that I also like talking about or discussing is data compartmentalization and statistics. And when I talk about statistics, I'm referring to things like statistical alarms. As you'll see during the course of what I hope is a conversation this morning, I am not a huge fan of absolute alarm thresholds. I think they have their place early in the life of a program, but I'm a firm believer that normal for a machine is defined very clearly and very individually on a machine by machine, measurement by measurement, detail by detail basis. And I welcome, opposing viewpoints, comments, criticisms, discussion, agreement as we go along. The other thing that is a huge topic for me is compartmentalizing data. And when I talk about data compartmentalization, I'm talking about making sure that when we collect data, we're doing it in a consistent manner from this time to the next time to the next time that we take data on a machine. Because we oftentimes run into a situation, especially on variable speed, variable load types of machinery, we run into a situation where the data may not be comparable from the last time I took it to how I took it today, just based on the way the machine is running, or the demands, the operational demands, the speed, the temperature, the pressure, the load that we're putting on these machines to satisfy our company's productivity and operational requirements. So those, to me, these two topics kind of mesh together, and so this becomes, like I said, my second favorite soapbox to stand on. So I want to begin this. Come on. We had this working a minute ago. There we go. I want to start with a question. And I would like this not to be a rhetorical question. And the question is, what is it we are really doing when we're collecting data periodically, either with a handheld data collector, with an installed scanning or surveillance system, or even with a full-time continuous monitoring system? What is it we're really doing when we're collecting data periodically? And I'll give you a hint. One of the presenters yesterday focused his topic on what I consider to be the right answer to this question. Anybody?
Looking for change.
Bingo. Looking for changes. That to me is exactly what this is all about. It's change analysis. We're looking to see, has anything changed? And really, what's the significance of the change? What is that change in the data trying to tell us about what's going on inside the guts of that machine? Do we have a change that's giving us an indication that we have a root cause failure mechanism for damage already in play, or something that has started? Or is that change telling us that the damage, the bad thing, has already started? And it's not a question of if, it's a question of when we want to take the appropriate corrective action. And from my perspective, we take that and then make the decision of, do we need to do anything? What do we need to do? When do we need to do it? And of course, continuing to, doing nothing and continuing to monitor it to see how things progress is also, a legitimate response. But the bottom line is, it's change analysis. We're looking for some kind of indication that we're deviating from normal behavior for the machine that we're monitoring. So the next obvious question is, what do we need to do to make sure that we're absolutely successful? And I've got a couple of attributes that we need to be considering. We need to have consistency in collection. We need to either have consistency in machine operating state, or we need to know enough about the machine's operating state so that we can say, this is how the data looks under this set of circumstances, this is how the data ought to look under another set of circumstances. We need the ability to flag and recognize that a change has taken place, and then, of course, we need the skills, or we need to have access to the skills for the folks who look at it and interpret that change and can say, this is good, this is bad, this is indifferent in between. Now, one of the things that we flash back to, and I was doing a little bit of historical looking through my, my library at home and some of the archives. And one of the things that I think really helped at the beginning of our industry in terms of the condition monitoring and evaluation industry is the vibration severity chart. And the earliest example of this that I could find came out of a training manual that IRD Mechanalysis published. The version I have is a 1994 publication, but I mean, they first put this out, I think, sometime in the 70s. And, oh, I'm sorry, I forgot where I was. There you go, I think that should be it in the metric system. I do find it a little odd that in the US, we're the last country to hold on to what we refer to as the English system. And if you go to England, they will be using the metric system. It confuses me sometimes, but at any rate, what IRD did is they put out this vibration severity chart, and basically it says, as a function of a particular frequency, what's a good target for a machine to be operating at? And I think over the years, people have kind of bastardized the intent of what this chart was supposed to represent. When it was initially put out, IRD was recommending that people use this as a target. This is a target for a new machine, or a recently rebuilt machine, or a machine that's just come out of maintenance. Over time, people kind of morphed it into saying, okay, this chart says, you know, for this particular running speed, this vibration amplitude is very good. And this vibration amplitude is very rough, and therefore it's very bad. And they tend to focus on these as absolute numbers. You know, thou shalt not exceed this value. Or if it is this value, it's really bad or it's really good. And I've found over the years, and I'm sure most of you have too, that that's rarely the case. You know, you just can't take these guidelines as absolutes. And one of my favorite examples is the US nuclear industry. When I was working at a nuclear power plant in the early 90s, our technical specifications required, and in the US, being the English system, the specification clearly stated that no machine shall vibrate greater than 0.325 inches per second, which if I did the math right is 8.32 millimeters per second. Somebody who's better at math than me can, you know, tell me how accurate that is. And it had to be measured in the band from the lower of 1/3 running speed or 10 hertz up to 1 kilohertz. This was the threshold that if I was out monitoring machinery in the nuclear plant, that's the threshold that by regulation, I had to make sure that all of our machinery complied with. Now the corollary, you know, so that if anything vibrated more than 0.325 inches per second, I was required by regulation to do some level of additional evaluation and make some kind of corrective action recommendation. Doesn't matter what machine it was. The corollary to this, and this is where it really got screwy in my mind, the corollary to this was the unwritten interpretation that was always popular. If the vibration is less than 0.325 inches per second, it must be okay. And I mean, everybody in this room can agree with that, right? I don't think so. And in a couple of instances when I was working at the plant, I had to do that battle. And as condition monitoring, you know, analysts and experts that we all are here in the room, I want to share with you an example of a machinery situation that literally happened to me based on this philosophy that if it's over 0.325, it's bad. If it's under 0.325, it's good, don't bother me, I don't want to hear about it kind of approach. I had 5 identical pumps, all in their own dedicated pump house. These were general service water cooling pumps that basically drew the water out of the lake, ran it through a pretty coarse filtration system, and it cooled all of the auxiliary equipment in the plant. I mean, it didn't feed the condenser. It just cooled. It was chilled water cooling for all the auxiliaries. These 5 pumps, I guess I should preface this by saying when I got to this nuclear power plant, the plant had been in operation for 7 years already. These were the relative amplitudes of each of the pumps, numbers 1 through 5, left to right. And over the course of the previous 7 years before I got there, these amplitudes were pretty rock solid. These pumps ran 24/7, 365. They each had their own individual vibration profile. And even though, I think that's at the 1, 2, 3, the number 4 pump vibrated a lot more than the others did, it was well below the magic 0.325 inches per second threshold, but it had been doing that and behaving that way since it was first started up. And so even though you can see a relative difference between the individual units, in this chart, I wasn't concerned about it. There was no indication of distress on that machine, no indication of distress on any of the other machines, because again, each one individually had been maintaining its level, the status quo, over the previous 7 years. And for the 5 years that I was there, they continued. Now, I don't know what happened after I left, but I'm sure nothing bad happened, even to that one guy with the highest vibration. I pulled into the plant one morning, and I typically parked my car right outside of this building, and I heard the most bizarre sound coming from, what was clearly one of these general service water pumps. And in a nuclear plant, you always have at least 2 sets of everything. One for inside the nuclear area, and one for outside the nuclear area. And when I was outside the nuclear area, I used the data collector that I literally kept in the trunk of my car. So I got out of the car, I put on my hard hat, I grabbed my data collector, I went in there, and I took data on the number 3 machine, and that's the relative amplitude that I found. I mean, and the thing just really, really sounded nasty. Couple things I would like you to notice. The amplitude on that number 3 pump increased by pretty close to a factor of 2. And recognizing the fact that I parked in the same spot every single day, the fact that I hadn't heard that noise Wednesday night when I left the plant, and Thursday morning when I came into the plant, I heard this, really, really nasty noise, and I went in there and I took that data, I kind of considered that factor of 2 increase was probably something pretty significant going on. But the interesting part about it was, as you can see in this chart, even though the number 3 pump increased by a factor of 2, its problem amplitude was still below the amplitude of the number 4 pump. I called the control room. During this particular time of year, we did not need to run all 5 pumps simultaneously. We were only running 4 of them at the time. I called up the control room on the phone and I said, hey, to the shift supervisor, I says, Gene, you've got to take this pump out of service and put the other one, and I don't remember which one it was, but it doesn't matter, but take this pump out of service and put the other one in. I said, the vibration's gone through the roof, something's wrong with it. And he says to me, well, Bob, what's it shaking at? And I don't remember what the exact number was, but it was something like on the order of 0.25 inches per second. And I says, Gene, it's up to 0.25. And he, honest to God, said to me, but Bob, that's below 0.325. How can I justify making that change? And I was just dumbfounded. I said, Gene, this is what you pay me for. The machine has for the last 7 or 8 years has gone at the same profile. And finally I said, listen, and I held the phone in the direction of the pumps. Can you hear that sound? He says, well, yeah. I says, well, this is what it sounds like. I said, it's going to hit 0.325 inches per second for, when it continues to increase. In the very near future, if you don't take it out of service and put put the other pump in service, it's going to hit 0.325 for about that long. And then it's going to get really, really quiet because it's going to have come to a screeching halt. Okay, Bob, I'll send a guy down to do it. It's like, how many have anybody else had that kind of experience? I mean, to me, it's fundamental. We're looking for changes. We're looking for changes that, that indicate something bad's going on, and we've got to react to it. And if we don't react to it, like I said, it's going to go, going to get real quiet, and everybody's going to be happy because it's not going to be making noise anymore. Of course, it's also not going to be pumping water and supporting the, the cooling load inside the plant. But, that seems to be a secondary issue when it wasn't vibrating at 0.325 yet. I have another example from my nuclear plant. This is not actually an example that I was involved with personally, but it was the example that got me hired. It got me hired not because of me, but because this particular incident basically caused my predecessor's head to explode, and he said, I just can't work here and can't do this anymore. Silly me, there was a job opening and I took it. But this is, and I don't mean to impugn anybody who was at the facility at the time, other than to say Craig was right all along, but plant management at the time chose not to believe him because they kind of felt that when he was identifying problems, they kind of accused him of crying wolf a lot. And unfortunately, he was right like 99% of the time. So they're trucking along, and they've got indications of vibration on some machinery in the control room. And what they're looking at is the overall vibration amplitude. So as time marches on, they're looking at this, I mean, it varies a little bit. But just for the sake of simplicity, we'll treat it like a straight line. All of a sudden, one day, they noticed that there had been a change. There was an increase in the amplitude. Step change. And it leveled out. And it ran that way for about a day. And they're acting like chickens with their heads cut off, going, oh my God, something bad happened. We really got to pay attention to this because the amplitude on this guy, it's gone up, it's almost doubled. They would think about that sometimes. It almost doubled. It's stable. And, we're really kind of concerned about it. So, of course, they got in touch with Craig, and, Craig knew about it already, and Craig's trying to, work out what's going on. The very next day, I mean, that's a period of approximately 24-ish hours. The very next day, this happened. So what do you think the response was? We dodged a bullet here. It got better. Now look at this, okay? If you start out with where the vibration started, it doubled. After a day, it went down to approximately half of what it originally was. This is a good thing, right? Vibration went down, right? I mean, come on, we're all vibration people. This is good. How come I don't see any heads nodding to the vertical except mine? This isn't good? Too much of a change. Well, and that's the funny thing about it. Craig did a little bit of the math, and obviously there's a couple of pieces of data that I have not been completely forthcoming with. This was on one of the low-pressure turbines on our main turbine generator, a 1,200 megawatt steam turbine generator. And all they had in the control room was the amplitude. Craig also had access to the phase data. So for those, forgot to click that in, oh well. Basically, I think we all know intuitively when I start telling you a little bit more about the machine, two bad things happened. If we look at it from the polar plot with the vectors, that's where the imbalance was initially. And it had been running that way for quite a while. On the first event, the imbalance vector moved, not too much in terms of the angular position, but the amplitude doubled. The third event, or the second actual event, was significantly more than the first, as we can see, when we look at it on a polar plot, looking at, considering the phase and everything, but the end result of the second event being clearly the more significant of the two events, but the overall amplitude ended up lower. So people that only understood things in terms of what the amplitude was said, it got better. Craig is running around going, no, 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 you don't understand. These things don't fix themselves. In reality, the first step change was a single blade loss on the fourth wheel. The blade that broke was actually about the size of this clicker. The next day, the event that happened was two blades on the opposite side of the wheel. So it's like it kind of tried to balance itself back into, I could just see the turbine rotor as it's going around going, oh no, that wasn't good. I better shed a couple more over here to bring it back down. Plant management was happy. Craig's going, you guys don't understand. And he's showing them the polar plots, and like I said, his brain just about exploded, and he said, fine, I can't deal with this anymore. Excuse me. Craig left the company, got another job at another nuclear facility. It was not the one I talked about yesterday that he went to. But when they posted the position, I applied for the job. They were in a refueling outage, and they had this thing open when I got there. And to look at it and see, and I had become aware of the situation, when I showed up on the job, this is why Craig's not here anymore, because, blah, blah, blah. And they said, well, we're opening up that unit today. Let's go take a look at it. It was exactly what Craig had predicted based on the vibration data. One small blade on the fourth stage and two small blades 180 degrees out on the other side. The point of all this, change is bad. I don't care if vibration goes up. I don't care if it goes down. And there are so few people that I deal with or have dealt with over the years that even consider using below alarms. Everybody looks at above alarms. Not many people look at below. But just based on this experience alone, there's a lot of value in recognizing this is good, this is normal, this is how everything typically behaves. We all agree that if it goes up like this, it's bad. I think we should all agree that if it goes down like this, that's also bad. But we seem to be, as a community, so conditioned to focus on keeping the levels below the thresholds that sometimes I think we as a community tend to forget. Our focus really does need to be on change. So I have put a new commandment. There's now 11 commandments, in case anybody's keeping track. And the 11th commandment is related to thou shalt not exceed. And as I said before, I'm really not a big fan of the thou shalt not exceed approach to vibration thresholds or any condition monitoring criteria, with a few exceptions. And basically, when you have a situation where your machine, you have some level of regulatory compliance, you may have a machine that's under warranty and the manufacturer or the supplier says, I will only warranty this machine if you make sure that the vibration stays below a certain level, then these are appropriate uses for a thou shalt not exceed criteria. Insurance requirements, part of, interestingly enough, when you look at the regulatory 0.325 inches per second being the threshold of concern for machinery in a nuclear power plant in the States, that's also an insurability requirement. If you've got a machine that exceeds 0.325 inches per second and you don't address it, not only did the Nuclear Regulatory Commission want to have a little chat with us and were happy to impose a fine if we didn't, respond appropriately in their opinion, our insurance carrier would up our rates because of the perceived increase in risk. We talk about manufacturer recommendations. I think absolute thresholds are good if you go back to the original intent of the original IRD severity charts. It's a great target for new, rebuilt, recently maintained, restored to service machinery. And I'm a firm believer that there is value in an absolute value threshold with a new program where you don't have any experience on a particular machine. I mean, you've got to start somewhere. You've got to have some threshold of concern. There are recommended amplitudes that you can use. You can follow the ISO guidelines. Technical associates, I know there's a number of folks that are a big fan of the proven method that Technical Associates recommends, and they've got bandwidths and amplitude thresholds. For folks that are new to condition monitoring and evaluation, at least from a vibration perspective, I think the proven method gives you a really, really good starting point. I think the ISO amplitudes give you a really good starting point, but I firmly believe they should only be treated as starting points. Because if we took a look at the statistics, for example, on those 5 general service water pumps that I talked about earlier, what you would see is, in all cases, they were well below the, I keep forgetting there's a monitor here. I keep looking over my shoulder. I'm so used to speaking and having my slides behind me that they're right here, and I just keep forgetting to look. So I apologize. I apologize for that. But basically, 3.325 inches per second was way above where these units were. If you looked at their normal variability, these yellow and orange lines that are surrounding the bands of each one of the machines, these machines, as I said before, their vibration stayed in a very, very tight range. And I'm a firm believer that once you have history on a machine, and this applies on a location, sensor by sensor basis, measurement location by location basis, and specific measurement type to specific measurement type basis. Consistency. When you've got the consistency that you need, and you know you've got it, focus on the statistics, because really this is all change analysis. If I'd had access to the software, and I was actually doing this when I was there, if I'd had access to the software, I think if I pushed a button one more time, you'll see how the number 4 pump that had doubled in amplitude overnight clearly would have hit my alarm report if I'd gotten that far, but obviously I didn't get that far. I'd only just gotten out of the car when I went in and took the data to figure out what was going on. But I am a firm believer that if you're not using statistical alarms, both above and below, you're probably missing out on the opportunity to identify problems a little bit earlier. And remember, like I said yesterday, what we are is we're a planning tool. We provide meaningful planning information to our management teams. That's the real value that I think we as a community bring to our employers. Or if we're consultants, it's the real value that we bring to our clients. One of the other things that I'm not a fan of, except, again, at the very beginning of a program, I am not a fan of combining data from theoretically identical machines into the statistics and saying, I've got a population of 100 of these identical machines. And so I'm going to statistically combine all these machines into, a single set of statistical thresholds. And just based on this experience alone with 5 identical pumps, what I've found over the years is that when you go to apply statistical thresholds, instead of focusing on, this measurement at this location and just doing statistics on it, let's just lump all the machines together and apply the same statistical criteria to those machines. This is what you end up with. you end up with a set of statistical criteria that is so wide that it's of no value. You may as well go back to the absolute value thresholds. Now, granted, this is my personal opinion, but I base this opinion on close to 35, years of doing this kind of work. That never would have exceeded if everything had been lumped together. The other thing that I feel very strongly should be avoided, and I've seen this done in a lot of cases, and you end up with a very similar result, is if you consider taking data on the non-drive end of a motor, you take data in all three axes, and then statistically combine those. I would urge you very strongly not to do that either. Alex, comment? No. Not a good thing to do. Because again, you make your statistics so wide that your thresholds of concern are so wide that you miss the subtle changes. And what's the key to the subtle changes? The subtle changes are the ones that hopefully are giving us what we need to know in order to be more proactive than reactive. Giving us the indication maybe that a root cause failure mechanism has started. And if we can address that root cause failure mechanism before the irreversible damage starts, we're right back on, looking at things from a proactive perspective rather than the predictive/reactive perspective. The other part of this, though, is making sure that when we take data on machines and do our statistical combinations of things to come up with reasonable thresholds that are representative of true changes in the condition that we're monitoring of these individual machines, is to make sure that we're taking data consistently at consistent operating states for the machine. Specifically, machines that are fixed speed, fixed load, they're running at 3,600 RPM minus slip, 24/7, 365. They're always pushing the same fluid at the same temperature and the same pressure. Not a lot of variability there. Excuse me. When you're dealing with variable speed machines, when you've got a machine that may operate at multiple different discrete speeds, like slow, fast, or slow, medium, fast, I think we all know intuitively it doesn't make sense to take data on a machine running in slow speed and combine it and compare it with data with the same machine running at fast speed. I mean, unless you're trying to do some real, deep diagnostic evaluation. For general trending and condition monitoring and evaluation and alerting purposes, you really don't want to combine these two states together, because the vibration profiles are likely to be extremely different from one to the other. Similarly, when we've got machines that operate under variable loads, we need to be conscious of what the load is when we take the data. Now, I know we rarely have the opportunity to grab our data collectors and walk out into the field and say to the operations superintendent, hey, I need to take data on this thing, but I need it to be running at this condition. Ops is going to look at you and say, yeah, and I've got production requirements. I'm not changing how I'm running that machine. You have to live with how this machine's operating today. So what does that mean? We owe it to ourselves to record a few other parameters in addition to the vibration data. I need to record the speed. I need to record the load. I may need to record several other parameters in order to assure myself that I'm putting myself in a position to compare data from consistent operating states from one time to the next. And if I took data today, it might be at one speed load condition. I take data tomorrow, it might be at a different speed load condition, et cetera, et cetera. But eventually we would get to the point where we've got some, enough data at each of the normal speed load conditions to be able to statistically compartmentalize them and then combine them so that we can do the appropriate thresholding, and again, focus on change. Because we want to make sure that when we see change in the data, we're seeing change in the data because something in the machine has changed, because that's really what we're looking for, as opposed to all I'm seeing is the fact that we've changed how we're running the machine today because we're running at a different speed or a different load condition. The other thing that we need to be able to focus on is intermittently and cyclically operated machines. We need to make sure that when we're looking at these types of machines, we're taking data consistently during the same part of the operating cycle. And one of my favorite examples of a machine like this would be a crane. Making sure that when we're taking data on the hoist drum bearings, we're always taking it consistently when it's loaded at a certain level and it's drawing up, as opposed to when the hook doesn't have anything on it and it's just lowering down to pick up a load. Simple things to think about, but we really, really need to focus on what it takes with our individual systems to make these things work. I have another example of from the nuclear plant that I worked at, because it I think really drives this point home, and I'm hoping this is more review for everybody than anything else. But the plant, I don't need to say, I already said that stuff. The plant that I worked at had a steam-driven reactor feed pump turbine. It was similar and, in fact, identical to, it's a de Laval unit. It's identical. There's thousands of these things in use all over the world. They feed nuclear reactors. They feed coal-fired boilers. And during their operating range, from roughly 0 to 5,200 RPM, this machine goes through two critical speeds. And we all know we like to avoid running on the critical speed during normal operation, but because it's a variable speed, variable load machine, it could run anywhere within that speed range. And generally speaking, if I remember correctly, it would, normal operation was really something like from 1,700 through 5,200 RPM. But in that range, like I said, what I've got identified as a normal operating range, there are two critical speeds. So the question is, what do we use for a threshold to identify when we have a problem on this machine? And I would say, well, it depends, where are we running? Where on this curve are we running today so that we can identify what's normal and then, what the real change is? Because suppose, for instance, I should have mentioned that. The manufacturer recommends on this particular machine that prolonged operation above this absolute threshold is not recommended. Not abnormal, they don't want to see you there, but it will run there. And this becomes a question of, is vibration an indication of a problem, or is vibration a problem in and of itself? And what the manufacturer says, basically, if you're running, you really need to avoid that area by the first critical speed, simply because running at that kind of an amplitude, we don't want you to do that, we're not going to warranty it, and all that blah, blah, blah. But really what I was hoping to do was, and there was the absolute thou shalt not exceed value. But what happens when you're running at this speed range? Basically halfway between the two critical speeds, when vibration is really in the machine's sweet spot. Suppose you're operating at that amplitude today, where the X is. Does that indicate a problem? I think we can all agree that it would indicate a problem. But for the more simple approach of putting in an absolute value threshold, where do you put it? Chances are pretty good, and in my experience at the plant that I worked in, it was the thou shalt not exceed criteria that the control room focused on. They would focus occasionally on the lower criteria where we say, we don't want to run more than like 10 minutes at this amplitude. But what about when we're running in the middle? we could have a serious problem at that particular point on the operating curve, and the alarms wouldn't even come in. And I use this as a very simple example that I think, it's probably a much lower level example than most of us in our experience and our skill sets warrant in this room, but I just, for the sake of example, I like to keep it really, really simple. So when you've got that kind of situation, how do you alarm on it? How do you identify to somebody that, hey, something's really, really wrong, even though it's well below the absolute value threshold that we've identified? And I think we can all agree and all recognize the fact that when we start chunking up the operating states of the machine into specific speed ranges, in the case of this scenario, we can then start to apply, or we can put back the other thresholds, but now we can start saying, I want to alert or alarm on this machine when it's in this speed range at this amplitude, but if it's in another speed range, I want to alarm and alert at a much lower amplitude. And this is what I refer to when I talk about compartmentalizing the data, focusing the data on the specific operating state and doing your statistics and your statistical alarming based on what's normal for this machine at this speed, at this load, operating under these very specific circumstances. Now, we've all, I'm sure, everybody in this room has worked with Bode plots and things like that, and that's kind of what I'm trying to represent here, so that, again, we chunk it up into specific operating states. It's pretty easy to do. Did I put that on? So, clearly we see that if we're operating in that mid-range with a set of alarm thresholds like this, that would absolutely grab our attention. And then we can investigate and, figure out what's going on. It's pretty simple, though, when we do this, and I consider this to be like a one-dimensional compartmentalization, because really the only variable that we're dealing with is speed. But it gets a lot more interesting when we start going to other factors. For example, consider a conveyor or a lifting device or a robotic type system where you really have four states. You've got a forward and a reverse direction at a high speed and a low speed. We need to start thinking in terms of controlling when we collect the data so that we can put them into these compartments. And now we're dealing with this particular machine, we're dealing with four sets of statistical criteria. And speed may be a factor. When we get into other machines, perhaps what I would consider the independent variables that we would use to help us determine what's the appropriate set of thresholds and where does this particular measurement today lie within the operational compartments and what statistics we apply, we can see that it starts to get more and more complicated. And the good news is, and when we can get to 3 dimensions and 4 and 5, and I'm just not good enough in PowerPoint to draw a 4 or 5 dimensional figure to illustrate it as an example, but you can see that we start increasing the number of possibilities. And the good news is our computer resources today are so much better than they were years ago when we first started doing vibration-based predictive maintenance monitoring, and it was all on DOS-based computers, and you just couldn't do this kind of math in a reasonable period of time on your desktop computer. I mean, face it, this dopey little cell phone I have in my pocket has a ton more computing power than some of the earlier PCs did. In fact, I think it's got more computing power than my laptop. I just haven't figured out how to use it all yet. But you can see that as we start compartmentalizing data, it becomes a more complex problem. But the good news is, with our computer systems and the software, the condition monitoring and evaluation software that's available today, I would say just about all of the suppliers in the market have the ability to compartmentalize the data based on machine operating state and the ability to generate and apply statistical alarms to give us a much better look at what's changing so that we can focus on what's changing and decide for ourselves, is this a meaningful change or is this something that we can easily explain away? And for those of you that have ever been in a paper mill, paper machine is one of my favorite examples of variable speed, variable load, variable, a whole ton of parameters. One of my better customers back in the States is a paper machine where they make two products. And it's the same machine, it's the same parts, running at the same line speed. You can tell, I mean, I can't, but the guys that work there can tell when they walk in the building first thing in the morning, they can tell by the difference in the sound if that machine is making bathroom tissue or kitchen paper towels. And when you go out with your vibration data collector, because you've got different nip pressures, and I mean, there's just so many different parameters that affect how that machine sounds and how that machine vibrates, that there is just no possible way to do any meaningful condition monitoring and evaluation without knowing the nip pressure, the speed, the temperature of the feedstock, the viscosity of the feedstock. It's just amazing. And like I said, it's like a night and day difference, they tell me, in the sound when you walk in the building. Oh, we're making bathroom tissue today, or kitchen paper towels. And when you recognize those changes and those differences, for me, it really starts to make sense to focus on compartmentalizing your data into those chunks, those consistent operating states and consistent operating conditions. And then once you've chunked your data up into those consistent statistics, then you're able to do what I consider to be the appropriate level of change analysis. Anybody have any questions or comments or concerns at this point? I only have a couple minutes left. I want to blast through. We're going to skip one more slide. We don't need to talk about that. We really don't even need to talk about this or this. I want to conclude with the various corollaries to the 11th commandment. Appropriately written, alert on thou shalt not exceed absolute thresholds sparingly. Collect thine data rightly and with great consistency. And compartmentalize thine data and use statistical alerts to help you identify the changes that are hopefully meaningful and do the right thing. Any questions, comments, concerns, issues, disagreements? Feel free to disagree. Yeah. Yes, sir.
What happened with the World Cup? What actually
That's kind of a funny problem. I'll give you the 90-second version of what went on with that pump. The lube oil guy almost lost his job as a result of what happened for the wrong reason. What had happened is operations had drawn an oil sample and it got sent off to the lab. The sample came back from the lab. The lube oil guy looked at it and said, this is great. Everything's good, move on. Good sample, no metal, no particulate, viscosity's right. Everything's good with the oil in the upper motor bearing reservoir. A couple days later, we had this problem. When we were doing the investigation, after they changed it over, what's going on, what's the problem, they drew another sample of oil, sent it off to the lab, and it came back. And when we got that report, they said, to Pete, who was the tribologist on site, they said, how could you miss this? This is horrible. There's, this particulate, that particulate, all sorts of stuff. And we're talking a time span of much less than a week. And I'm gonna pose this as a non-rhetorical question to you guys. What happened?
The oil level too much with the sample, first sample that came out.
No, actually, both samples were legitimate. The reports were legitimate with respect to the samples that were sent out. The initial sample, everything was good. The follow-on sample, after we shut it down and, we could see in the spectrum, all the problems going on in the bearing.
First sample was actually from a different pump?
First sample, no, it was all good. Think about the sampling process for a minute.
One was running?
Nope, it was think about the sampling process. Somebody goes out to a pump or a machine, draws a reasonable sized sample out of a relatively small sump. Fills the jar, caps it, writes the label, grabs a lubricant and replenishes what they just took out. There's a clue here. He put the wrong stuff back in to replenish what he had taken out. At that time, the plant had no really good control over what lubricant went in. Let me back up. They had good control of what lubricant would go into what machine if they were doing draw it all out and replenish the whole thing. But they really didn't have the appropriate training and the appropriate controls in place to make sure that when you draw a small sample out and you go to replenish that small sample, that you make sure you put the same stuff in that you just took out. And this is where plant management really went nuts on the lube oil guy, because all of a sudden, the viscosity of the initial sample that was good, was this, the viscosity is now that. And you start looking at some of the other parameters in the oil, clearly this is not the same stuff as this, because it had been diluted with the wrong stuff going back into it. And that's actually what led to the problem. Anybody else? Question? Yes?
Yeah, I had a question about your self-healing nuclear power plant pump.
Well, that was a turbine that was self-healing.
Right, the shielding. So the shielding blades, did you find fatigue issues all around, or was it?
Actually, there were fatigue issues all around. The sad story about that turbine is when they contracted to build the plant, that machine was available. And is power here 60 hertz or 50 hertz?
50.
Okay, 50 hertz power here, 1500 RPM would be on a big steam machine like that. We're 60 hertz power in the US. That machine was identical to a number of machines in other parts of the world where they operate on 50 hertz power. They got the machine for a good price, it was available. I truly don't think anybody paid close enough attention to the fact that every other use of that machine, except for two, there were two others that were put into the US, and they had similar problems. They had similar, hello? Everybody hear me okay?
Yes.
They had similar problems at the other nuclear plant.
Just grab that.
Yeah. They had similar problems to what we experienced at our plant at the other nuclear plant in the US that had the same machine. They got it for a good price. It was available. It's that low bidder thing that we all get concerned about so often. If you looked at a run up and a coast down on this machine, the quietest, the calmest part in the spectrum was when you were running through 1500 RPM. And at 1800 RPM, for supplying 60 hertz power, you were actually on the upslope side of the second critical. So what ended up happening, and we discovered during that refueling outage when I arrived on scene, had nothing to do with me being there because this was already underway. When they opened it up, they saw that, sure enough, one blade over here was gone, two blades over here were gone. They started looking and they opened up all the hoods and they looked at all the turbines, and there was a pretty consistent manufacturing defect at the blade root. And so what they did for the short term, because they didn't have time to get a whole new set of blades, they literally pulled the fourth stage out of all three of the low pressure turbines on both sides. and put blanking plates in there because that got us back online. We were, I would say, 5 or 6%, reduced on our power consumption, but at least that gave the opportunity to have new blades remachined. But it turned out to be a problem. We immediately notified the other plant in the U.S. that had 2 of these identical machines, and during their next refueling outage, they popped the hoods and pretty much found the same problem developing on their units. And they did the same thing we did. They pulled out all the 4-stage blades on both sides of all 3 of their, or actually all 6 of their low-pressure units, put in blanking plates, and used the same manufacturer we did to create new blades.
Any other questions? No? Well, I'd ask you to put your hands together for Bob's presentation.